Well, hello everyone. Welcome to Lambda Calculus Video 1 Machines to Machines. Hello, my name is Hua and this is Computation Learning Center. First of all, motivation. What's in it for you? So what's on the table? So in this video and in subsequent videos in the series, we will be exploring about methods. So why should we do that? There are two advantages to doing this. The first is philosophical. What is a valid description of a method? What can and cannot be done by computers? But if you don't really care about philosophy, we have also practical stuff as well. First of all, you can learn more about programming. And if you already know about programming, how about functional programming? And if you're into that, who should watch these? Well, anyone who's interested in the things I talked about earlier. I intend to keep it fun and visual and light-hearted, and it probably will get more detail later, but I'll keep it simple for now. So without further ado, let's jump into it. Story time. So in high school, we're all stuck in math class, and to me it was just a bunch of problem solving and we apply a bunch of equations to some random problems. For example, like if you see a sine, then do this, and then if you see a circle with a tangent, then do that. There is generally no rhyme or reason to what we do and when we do it. But in my 9th grade, like when I was about 15 years old, one of my teachers was really adamant about having a method to do everything. So in college, I researched a little bit more about computation, and I came across this book called Introduction to the Theory of Computation by Michael Zipser. And in there, to sum it up, basically it says that that's a bunch of BS. Like, there is no method to do everything. So yeah, let's get a little bit more philosophical and try to define what we mean by computation. First of all, what is computation? Well, simply put it, computation is a kind of action. For example, when we slice an apple, we see that we apply the action called slicing to the object apple, for example. So to be more precise, when we say an action, we mean that something is changing, something is moving, is evolving in time. But are all actions just computations? Well, not really. First of all, the subject, that is the thing doing the action, must follow steps and then obtain an output. Exercise time. Which of these are computations? Number 1, eating a banana. Is that a computation? Well, no, there is generally no method we abide by to eating a banana. I mean, really. And also the most important thing is that there is no output. What is supposed to be the output when we eat a banana? Banana peel? I don't think so. Next, writing an essay. Is that a computation? Yes, of course, you go online and you copy and paste something from Google. No, I'm just kidding. It is not a computation. there is no method to writing an essay. So third of all, reading. Is it a computation? Hard to know, but according to me, it is a computation. There is the method to reading. You read word by word, line by line, paragraph by paragraph, for example. And then the output. Well, what is the output? It is kind of hard to know exactly what the output is. But you know, if you have the ability to open your mind, and you might be able to see that the output is the idea of the book from text form going into your mind in like brain frequency form, if that makes sense. Yeah. Okay, finally, is thinking a computation? Well, I don't think so, because first of all, there's no method, and also there is no goal, no method to abide by. So I don't think that is a computation. Alright, so let's talk more about methods, that is the how of computation. So earlier I said that in order for a thing to compute, it must be following steps. But what does that mean? What does following steps mean? What constitutes steps? And for example, we have a problem. I give you a letter in the English alphabet and you convert it to uppercase. So one might go about doing that by setting up a table right here with 26 rows. Each row on the left is a lowercase letter, and on the right is the corresponding uppercase letter. And then when you give me a letter, I go here, I look it up, then I give you back the result. Okay, so table, that is. Can we actually apply the tabling method to counting? For example, I can give you like 3 things, like a circle, triangle, and smiley face. Can you tell me how many things are in this collection? Well, if we actually sit down and make a table from it, we would see that we wouldn't be able to finish writing the table, right? Even if we can somehow find a way to look it up, we don't really have the table. So yeah, this doesn't work. So how do we count? How do we actually count? Well, you know how to count. For example, if we have 3 objects right here, 3 cubes. First of all, we start from the number 0. We have 3 things from the right, and then we take one and push it to the left like this, and we increment the number. Do it again from the remaining objects. Pick one to the left, increment the number to 2, pick an object, put it to the left, increment the number to the number 3, and then there's nothing remaining, so the output is 3. So one important thing to note is that methods must be really easy. So what does that mean? What does easy mean? Well, maybe some people say that easy means that any normal human being must be able to follow it. But, you know, depends on what you mean by normal. So from what we have seen, that these methods look pretty different. For example, one is via a lookup table, and another one is a step-by-step instruction. So they look really different, and the question is that what are methods supposed to look like? What do we mean by methods? How do we know when someone presents us something we can say, hey, that's a method? How do we deny that it's not a method? Well, we will answer that with Lambda calculus, a framework for defining methods. So let's meet the heroes of the story. The hero of the story is Alonzo Church, the author of Lambda calculus. Back in the days, he used to be the thesis advisor of Alan Turing, the one who invented the Turing machine. They do kind of the same thing, really. But we choose to follow Lambda calculus because Turing machine is kind of lower level, and it doesn't really help when trying to pursue the question intuitively, let's say. So what do we need for methods? First of all, we need a mean of abstraction. Abstraction means that we talk about a thing, but it can stand for many things. You see that this idea is applied in mathematics. For example, for all x is equal to x times x when x equals 1. We say that we introduce the variable x right here, and then we can use it subsequently. And these x all refers to the x that was introduced. Not just mathematics though, this idea is also available in natural language. For example, in the saying all that glitters is not gold, we can actually translate it to this mathematical form. For example, for all x glitters doesn't imply x is gold. That's probably wrong, but you know what I mean. But why do we need a mean of abstraction? For example, when we see the counting earlier, we were talking about cubes, but there is no reason why we have to talk about cubes. We can also talk about like spheres or pyramids or electrons, for example. And if we need to actually specify all of those things, all of those methods for all of those things, we would have to specify an unlimited number of methods, an unlimited number of things, you know. So it goes back again to the idea of an infinite table. We cannot really say that. And almost all method applies to an infinite number of things, infinite number of inputs. So we need abstraction. And then how do we write it down? Let's introduce a thing called a lambda expression. A lambda expression is an expression like an object in the lambda calculus, and you see that the entire rectangle right here is a lambda expression. And on the top we have a parameter, aka input, and on the bottom we have a body, aka output. So the parameter ties into the variable the abstraction we talked about earlier, it introduces a general object, and in the body we can have variables that refers to that parameter. And how do you know which is parameter and which is body? Well, you see this horizontal line right here. I call it the abstraction line, the line which defines abstraction. So, oh sorry, I didn't tell you which this function do. Well, this function is the identity function because, well, I didn't say how functions work, but you can see it has an input right here, and then it has an output which refers to the input, meaning that whatever is inputted will be outputted. You will see later how that thing works in detail. And another function is the function true, or so-called pick first function. So again, we see the abstraction line. So we have one parameter and one body, and this body is more sophisticated because it is also a lambda expression. So we have the outside expression and we have the inside expression covered in yellow right here. So this expression, we also see that we also have the abstraction line right here, and in the body of the inner expression we have a variable that refers to the outer parameter right here, that is the parameter of the outer expression. So yeah, the idea of the lambda expression inside lambda expression is kind of like Russian doll. You know, they are known that in a Russian doll you can have a smaller Russian doll. Inside of that we can have another Russian doll. So if you think of them as expression, we have this small expression is in this small expression in a bigger expression. So there's another function. We have the false function. So earlier we have the true function. It picks the first parameter. Now we have the false function which picks the false parameter. Same idea. And what else do we need? Well, we need a means of applying a method to an object. We say make the computation and then obtain the result. For example, we say in natural language, count my socks. What that translates to is apply the method named count to the object named my socks. Also we say name the star, and that means it apply the method name to the object the star. In general we have a notation right here, f of x. What that means is apply the method f to the to the argument x. So why do we need application? Why do we need to talk about applying method to an object? Well, you know, first of all, for convenience, because in a bigger function, for example addition, we need to be able to say, we need to be able to count, to be able to add add 1 to a number, for example. So in bigger function, we need to utilize smaller function to keep it short. And also sometimes we can have functions as abstraction. So what do I mean by that? It means that sometimes we don't even know what we want to do. For example, the f right here can be referring to a parameter introduced elsewhere. And when it comes to apply the method, we look up the parameter to know what we should do and then apply to x. Alright, so how do we write this down? So application is written in side by side like this. In the middle there is an application line, a vertical line, as opposed to the horizontal abstraction line you see here. So on the left we have a thing called the operator, aka the subject, the thing doing the action. And on the right we have another expression called the operand, aka the object, aka the argument, aka the thing being acted on. And we have already seen this expression before. This is the identity. It takes whatever it takes and then returns it. And this is true. It receives 1, 2 parameter and then it returns the first one. So another example, this time try to read it without my guidance. Ready? Alright. So this is an abstraction by the vertical line. Sorry, this is an application by the vertical application line right here. On the left we have another expression that is another application, and within that we have the operator being the function false and the operand being the function identity function. Oh, sorry. And then on the right we have the true function again. So to recap, this is an application of an application to the true function. So what else do we need? Well, nothing. That's it. Application and abstraction equals everything. Yeah, but what does that do? Well, I'll tell you right now. We need semantics to be able to know what these refer to. It autoplays. Let's see. So, for example, the application, as I said earlier, refers to doing a computation, and the computation has a method that is the operator on the left right here. Can I make it full screen? Yeah. Operator on the left, and the operator is the identity function, and it has a parameter right here. We can view it as a whole for its argument to sort of substitute in. So yeah, the argument, the operand right here is this function. So we substitute the argument into the parameter, and then as a result, after we have substituted in, I didn't tell you to play. No, it doesn't end. Wonder of technology. Oh my god. You know what? Maybe I should have viewed this offline. Too late. Too late. Too late. Error. So, what do we have? We have an application. So as I was saying earlier, an application signals a computation. The computation applies the method, that is the operand on the left, to the object, to the input, the argument, the operand on the right. So what do? We view the parameter of the operand like a whole, so that the operand can actually substitute in like this. So now what we say is that we have instantiated the parameter. What that means is that whatever refers to the parameter will be substituted by this argument, like that, just like that. And then finally we have done the computation. We don't need the method anymore, we don't need the argument anymore. We expand the body of the operator to be the entire result of the computation, like so, just like that. Easy. So next up, we have another application. This time we are applying this expression right here to the identity function. But however, this expression is not reduced to a method yet. How do you know? Because it is an application. It is a computation that must be done. You know it because of the vertical line right here. And so we must do that computation first. So this computation actually has a method on the left right here. So yeah, as before, we substitute the operand to the parameter, like so, and then we propagate the values to the variables that refer to that parameter, like so. And then we remove the junk that we don't have and expand this body to the entire expression, just like that. Then now what do we have? We can finally resolve this application right here, because we see that on the left we have a method that has a parameter that is not used anywhere, and we will see it because we can substitute the operand in, but then nothing happens because nothing refers to that parameter. So yeah, we just obtain the body as the result of the computation, and then that is done. So remember this. Remember this. This is the false function, right? It receives 1, 2 parameters, and then it returns the second one. So as I was saying earlier, we have the true function and the false function. We have the false function as the result of the computation, and actually that's right, because we apply the true function, which is pick first to 2 arguments, false and identity, and it picked the first one, which is false, which is what we had. So that's right? Next up we have the apply to self, the looping computation. So this is an application of a function called apply to self to itself. So this function apply to self receives an argument, and then it applies that argument to itself, like that. So without me playing the video, can you see what will happen? Maybe you can get some pencil and paper and check for yourself. I think if you actually see for yourself, it will be more interesting. Ready? Let's see the result. So we replace the parameter by the operand, and then we propagate it to these two right here, like that, and then we expand the body to be the entire expression, and that is the body. That at the end right here we have the computation looping back to the beginning. This is what you saw at the beginning. So now what the machine will do is that it will return, it will come back again, and it will continue looping. Loop. Like that. Keeps going. So what does it tell us? It tells us that not all methods written in Lambda calculus at least will hold. What that means is that if you have a computer and you tell it to run the function, then the CPU will runs to 100%. If you leave it for a day, then your computer will give in, probably. Alright. Interesting, huh? So now we're at the end. Thank you for listening. This video might have been a little bit more abstract, but we have more exciting things to come in the next videos in the series. For example, we can have numbers, we can have list, we can have recursion. So hope you join me for that. If you like the video, feel free to share, like, and subscribe. Credits roll.